Hello once again. This is the third video in the course Introduction to Control Engineering. And what I want to do in this course is to just present an overview of the entire course. Now, we've seen this diagram already. For a typical control system, many times this is what we have. We have a set point which we supply. We have a transducer that converts that set point into a signal that our system can use. Then we have a summing junction, and what we get back from our feedback transducer, we sum them together and send it into a controller. Maybe some disturbance comes or not, but then the controller sends a signal to the plant or the process to control it. And the output of that is our control variable, which is what we measure and send back as a feedback signal. Now, just to give an overview of everything we'll be doing in this course. Now, this course is relatively mathematical. Much of what we'll be doing in here is mathematics. And so really what we have is this. Now, we're going to review Laplace transforms. Now, I have the diagram out there, so we can always come back to it and see, okay, where do these things actually fit in? So we're going to review Laplace transforms. And the whole idea here is Laplace transforms what is in the time domain. Sorry, is in the frequency domain, and it's a way of, if you want, representing a system. We find out that Laplace transforms give us a way of representing a system in the frequency domain. Now, when we can do Laplace transforms, then we can find transfer functions of systems. Transfer functions of systems, if you want, transfer functions, transfer characteristics of the system, talk about their input-output relationship. In other words, what's the relationship between the input and the output? Put another way, if I supply a particular input, what would the output be like? So for example, we have a simple system that whenever I send in a particular input, the output is exactly twice of the input. So think of an amplifier. If an amplifier has a gain of 2, that simply means if I supply an input signal of A, the output that comes out will be 2A. If I supply 1 volt to the input, the output that comes out is 2 volts. So the transfer function of that amplifier is simply 2. Output divided by input gives us our transfer function. Now, if we can represent our signal in the frequency domain using Laplace transforms, for example, let's assume our input signal is a sinusoidal signal, a sine wave. Then if we can take a Laplace transform of that sine wave and we check our outputs, we know the Laplace transform of the output. Simply divide that output by your input and you have the transfer function of a system. Let's come back out. So what we have said is, if we have a simple input signal here, okay, and bring it in focus. If we have our input signal, we could take the Laplace transform of this input signal. If we also have the Laplace transform of this output signal, then output divided by input can give us the transfer function of this entire system. In the same vein, the control variable, or whatever comes out of the plant or process, if we have the Laplace transform of that and we have the Laplace transform of what comes in, we have the transfer function of this. Or, on the other hand, because output over input gives us the transfer function. On the other hand, let's assume we don't have the transfer function of the output, but we have the transfer function, we don't have the Laplace transform of the output rather. If we have the transfer function of this plant or process, like we said, for instance, an amplifier has a transfer function, the transfer function of the amplifier might be 2. If that is the case, then whatever the input is here, input multiplied by my transfer function tells me what the output will be. Now that is very useful. If I have the Laplace transform of my input, now the input I supply, so I can take a Laplace transform of it. If I have the Laplace transform of my input, and I know the transfer function of my transducer, and the transfer function of the controller, and the transfer function of the plant, and of this feedback sensor, then it means I can find the transfer function of this entire system, and I can determine that whenever I supply any particular input with a specific Laplace transform, I know the Laplace transform that will come out. I know the output that will come out. I mean, if I have the Laplace transform that comes out, we can always convert that back into the time domain. So we'll start with Laplace transforms. Just to review that, you've already done that in CH 305 and CH 306. So we just review Laplace transform just a bit because it's very important. If we can work in the frequency domain, then it is simple algebra. Literally, A times X is equal to B, if you want. Usually we'll have R or U as our input signal, and our output will either be C or Y. Many times that's what we'll use. So we could say that at the transfer function, well, we often will use G, or we might use T. In the forward part, for the feedback, we often will use H. So if we, let's say we use T here, then we simply say U times T will be equal to Y. Okay, U times T is equal to Y. So the input times the transfer function is simply equal to the output, and that's the beautiful thing. So that's why Laplace transforms are very important. Now, this diagram we have over here is called a block diagram. Okay, it's called a block diagram, but we'll look at block diagrams a lot more in the course. We'll look at block diagrams, understand them. How do we deal with them? Is there a way to, if you have the transfer function of several pieces, can we bring them all together and get the transfer function of the entire system? Now, there are ways of doing that, so we'll look at block diagrams. So all of that is in the frequency domain. Then we will also work in the time domain. In other words, instead of going to the frequency domain, our signal, we already have it in the time domain, maybe. So why not let's just work in the time domain? Can't we just simply model the system? Instead of finding transfer functions of the system, why can't we just model the system in the time domain? When we're modeling the time domain, we have what is called state space representation. So we'll find out how to obtain the state space representation of a system. And then signal flow graphs are one way we draw systems when we're working in time domain. Instead of working with block diagrams, we'll often work with signal flow graphs. So we'll look at signal flow graphs again, we'll look at minimization of signal flow graphs and how to obtain the gain of the system or the transfer function of the system or whatever, or how to work with the system if you have a signal flow graph. Having done that, we now want to do three things. And generally speaking, when you have a system, for example, when you have a system like this, one of the things you're often concerned about three things. How does this system behave? How will this system actually behave over time? We call that the transient response. How will the system behave over time? What will the stability of the system be? And will there be any steady state error? Now, those are the three things that are listed down here. Time response, stability, and steady state error. Let's just zoom back out and talk about these a little bit. Okay, so we're often, in fact, in most cases, we are very interested in knowing how will the system behave over time. So, for example, if you have a thermometer, the thermometer has a reading at this point in time. If I place the thermometer inside a bucket of water and I want to measure the temperature of the bucket, of water in the bucket, think of a mercury in glass thermometer. You probably have one at home. Think of that mercury in glass thermometer. If you put it inside a bucket of water, how long will it take before you can take an accurate reading from it? Now, that talks about the time response. In that case, that system, we know that the value of the thermometer won't suddenly jump. You have to take a little while to take a measurement. Now, how long should we wait? Okay, talking about the time response of the system, that defines how long we have to wait before the instrument gets to steady state. Okay, before the instrument gets to its steady state. In other words, before the output of the instrument settles to a final value. When it has settled to a final value, we can now take our reading. So I've used that instrumentation system there. Note, that's not even a control system per se. But then this whole concept we have in here are useful, not just when we are talking about control, but generally when you're talking about systems. If you want to do something with the system, how long will it take the system to settle? So, for example, we talked about the economic system in the last class, or in the last video. Now, if you had an economic system, what if I wanted to control it? If I supply a stimulus to this system, how long will it take the system to settle? So, for example, how long will it take? In fact, let's look at the pandemic situation we have right now. If we supply vaccines and we start vaccinating the population, how long will it take before you have herd immunity? How long will it take before we can reopen the borders? How long will it take before we can reopen businesses and co? Now, if you listened to news, one thing you would hear was in Nigeria, for example, when we had the first wave, when the numbers started dropping, experts were saying, yes, this was predicted. We were expecting that the numbers would start dropping. And then there was also that prediction that they were expecting a second wave. Now, all these are based on models and based on time response of the system. They've basically come up with mathematical models of the system, or at least some types of models of the system. And based on that, try to determine that, okay, this is how we expect the output of this system to behave based on the input, which is coronavirus. okay, or COVID-19. So it's based on that input. This is how we expect the output to behave over time. This is how things will be. So that is a time response of a system, and this is a very, very important thing that we are concerned about when we're dealing with systems, not just control systems. When we're dealing with systems, then you have what is called stability. Stability talks about how the output grows or doesn't grow over time. So, for example, if you have think about if you try to balance an egg on the top of a triangle, imagine that you had a triangle and you try to balance a ball on top of it. Now, that sounds very, very, very ridiculous. So, we have a simple triangle over here, and then we now decide that we want to balance a ball on the very tip there. Now, if the center of gravity is just above the tip, yes, the ball will remain balanced. But once you supply any input to any of the sides, what will happen? The position will keep on increasing. Now, imagine this triangle sides were infinitely long. This ball will keep on rolling, and the distance. So you supply a small signal, a small input signal, and the output position, let's say displacement is the output, the displacement will keep on increasing and increasing and increasing and increasing and increasing. This system we say is unstable because a small input, now I don't want to get too technical at this point, but a small bounded input is providing an unbounded output, that we don't have a limit to what the output is, literally. Like I said, imagine the sides are infinitely long. This thing will just keep on falling until a different input comes to stop it, which could be, if it gets to the ground, action and reaction equal and opposite, then that will now stop it from rotating any further. But that is a separate input. Based on this single input, small push that we give it, we have an unbounded output. This system we will say is unstable. Compare that instead to, let's say we had something, a shape that was something like this. Let's assume it has a flat bottom so that this will not rotate whatsoever. Now, if you had a ball somewhere here, inside the bowl, inside this, if you supply a little bit of force, not very much force, a little bit of force, what will happen to this ball? It will roll to one side a bit, then it will come back down and then go back, and in the end it will settle in this center. So the amount of displacement you have will not be much. It's a bounded output. Okay, so the output is bounded. You supply a bounded input and you have a bounded output. This system we could say is stable. Okay, we could say it's stable. Note that if your input rather exceeds a certain bound, you now have instability in the sense that your output now becomes unbounded. Now, that is typical of many systems. So we often want to study a system and ask, okay, let's say we want to inject a stimulus into this economic system. How will it behave? Will that suddenly create an unstable system? For example, will that create inflation? Now, this is something economists do all the time when they're trying to decide what should we do. Should we devalue the naira? Should we liquidate? Should we supply more forex into the market? Should we print more money? Should we not print money? Because the amount of money in circulation determines the inflation rate and all. So these are things they have to really consider about, okay, by doing so and so, we will make our system unstable. We suddenly have inflation that goes out of bounds. Now, this is the kind of thing that happened in Zimbabwe a couple of years ago, when the inflation was just simply ridiculous. I mean, the figures were ridiculous, where you needed millions of Zimbabwean dollars to buy just a loaf of bread, and you come back in a year's time, and the figure for buying a loaf of bread was even way more ridiculous than that. Now, the inflation was simply out of control. That was an unstable system. So what they had to do was now effectively just change. I don't want to go into economics here, but basically now stopped using the Zimbabwean dollars and instead started using the South African rand. Use that to stabilize their system. After their system stabilized, I think now they have ditched the South African rand, and now they're using the Zimbabwean dollar once again. But then now the system is stable. If an unbounded input comes in once again, that will create an unbounded output, and then one may have to worry about the system. So we've talked about time response. How will the system behave over time? We've talked about stability. In the end, will the output settle to something, or will the output just keep on growing without bounds? Then the third thing we talk about is steady state error. In other words, let's say I specify that I want this thing to go to so and so position. When it settles, let's assume the system is stable and it settles somewhere. Does it settle where I want it to? So remember one of the videos that I showed in the very first video, in the very first lesson. Say you had a dart board. So you wanted to throw a dart at a certain target. Okay, so you have a dart board. You are throwing at. You have a dart rather that you are throwing at a particular target. When you throw the dart at the target, you have a control system with feedback and everything, and you are expecting it to hit the bull's eye. What if every time when you throw the dart, if it does not hit the bull's eye or wherever it lands, you want to measure the distance between where it actually hits and the bull's eye, and that tells you what the error is if you want. Okay, that is your steady state error. So after your system has settled, what is your steady state error? Let me take another example. Let's say you had that our thermometer. Once again, you put your thermometer inside a bucket of water and you tell it to measure the temperature. You now take the reading after the value has settled. After taking the reading, it says the temperature of the water is 20 degrees Celsius. Okay, let's say you have another standard thermometer that was made by the gods and you know that this is definitely accurate. And that one says the actual reading is 20.5 degrees Celsius. Then you could say, okay, there's a steady state error in your own instrument of 0.5 degrees Celsius. It has settled down to its steady state value and there is an error in there. So that's a steady state error. And it's something you also want to consider because if you have a system and you supply a certain set point, you are hoping your control variable at the end of everything, your output will match this set points perfectly. But you want to know how well will your output match your inputs at the end of everything. Now, we've used very simple examples so far in this course. It is not always that simple. It is not always that simple. For example, think of your economic system. If I supply a stimulus of $1 million into Nigerian economy today, what will happen? If you're expecting creation of 1 million jobs and lifting 25 million people out of poverty, at the end of everything, when the whole system has settled, how many jobs were created, how many people were actually lifted out of poverty, that will be your, you can now use that to compare that with your set point and you get what the steady state error is. Now, generally speaking, take note that the reason why we do all of these studies, we are not just taking a system that has been designed and trying to analyze it. Rather, what we're trying to do is we know a plant, we have a plant that already exists, if you want, the Nigerian economy. It already does exist. Now, what we want to do is to design everything around it, particularly this controller. That's the most important thing that we often are trying to design. Trying to design a controller such that when we supply our set point and our reference, we get a particular control variable. Now, like I said, we can't always have zero steady state error. But generally speaking, we always, when we talk about the specifications for our system, let me back up a little bit. So when you have a system, when you're doing a control engineering design, you will start with a specification, okay? You'll be given a specification. This is what we want you to do. We want you to design a system that will meet so and so specification. Now, three things generally that will be in that specification. One, time response. So, for example, you want it to settle. You want it to get to a steady state within a certain amount of time. And maybe you want, when it is going to the steady state, it's possible that, let's say it starts from here and the steady state is somewhere around this position. But then it's possible that along the line, it first of all goes beyond that steady state, then comes back down, and then goes up again, and then comes back down, and goes up again, and now comes back and settles. Okay, it's possible that happens. Or it is possible, on the other hand, that it just goes straight like that to settle. It's possible it takes a short time, it's possible it takes a long time, and all of that. All these will be part of the specifications that are important when you're starting your design. Okay, so you need to know that stability, generally, we always want the system to be stable. So that's the second specification we're interested in. The third specification usually is we don't want a steady state error that is beyond a certain point. So those are three specifications that are usually very necessary at the start of a design. Okay, so once you have your system in control engineering, many times what we're trying to do is to meet our specifications. So you're trying to design a controller that will ensure that this entire system the transient response will be in a certain way. Okay, the time response, transient response will be in a certain way. For instance, it will settle within a certain amount of time. It will not, the percentage overshoot, it could not overshoot the final value by more than so and so. You want to make sure that the system is stable at the end, and then you want to make sure that after everything, your steady state error doesn't exceed so and so. So many times in control engineering, what we're trying to do is design this controller that will meet all of those specifications. But in order to do that, we have to first of all understand how to model a system in the frequency domain, in the time domain. Then we also look at how to characterize the system, transient response, stability, steady state error. Then in future course, not in this course, you now talk about the design of the controller itself. So in this course, really, what we're just trying to do is to understand this system, and it's a compulsory course for everyone in Elect because it's all the principles you learn in here are useful for any system. This is not really about control engineering. If you want, this is all about the modeling and simulation of systems. That's largely what this course is about. So yeah, so I thought that it could be a good idea to present a big picture to you at this point. Thank you. So we'll see you in the next video.